can hear
Hello,
you.
hello. Okay, hello.
Yes, sir, you're audible.
Okay, so give me 5 minutes. I will be reaching into my office. Okay, just give me 5 minutes. Okay, I'm going to my office.
Hello.
Sir is just moving to his office, like he was there, so he'll be back soon.
Thanks, Arav.
Hello. Yeah, just a second. Give me a second. Okay, sorry. Yeah, now I'm online. I'll share the screen and start the class. Sorry about it. Okay. Okay. Let me share the screen. Okay, that's what. So we were discussing about the. I'll just briefly cover the kind of outline whatever I taught last time. So we are basically discussing about the superconductivity, and superconductivity primarily is a phenomena which is different from a very good conductor. Okay, let me ask you, can you hear me? And
Yes, sir.
Yes,
Yes,
sir.
sir.
you are able to see whatever I'm showing, right?
Yes, sir.
Okay, good. Great. So yeah, so it's not just a simple better conductor or an ideal conductor. It's different from an ideal conductor. In a way, it's something different. Of course, we'll see. I mean, let me just go to. It's like a super as we discussed last time. So it has the property that below a certain temperature, which we call it a critical temperature, the resistivity or resistance goes to absolutely zero. And this is one of the two important properties of superconductors which you can define. So it passes through, like, there are no vibrations as such. There are no vibrations of the background atoms or ions through which the electrons can get scattering. So it passes through like there is no scattering, and important thing is without any voltage drop, the current can be sustainable, and then it can keep flowing for very long time. So this was just simply the background. Kamalion discovered it. We discussed these things in detail last time. So okay, that was like how was it discovered and how to measure it, how to confirm that it's really zero. You cannot simply check it by simply a voltmeter, because voltmeter would have a certain sensitivity below which you cannot measure. The same thing happened even for the Kamalions. He could not measure below micro ohms, so it was like going from like 1 to the power minus 1 ohms to 10 to the power minus micro ohm. So he used a kind of a different way technique to really confirm that the resistance is really zero through this thing. So there are two properties. One is zero resistance, and another one is this that superconductors expel the magnetic field from inside it, and it's not simply by like Faraday's law through which you can explain it. Actually, it's completely different in a way that even if you do not apply the magnetic field, there is no del B by del T, so the magnetic field does not change as a function of time. Even if you apply the magnetic field in normal state and then cool it down, and in that process, since magnetic field is not changing, so magnetic field should remain inside the superconductor. But actually what happens that even in that case, the magnetic field gets expelled. So this is not a normal electrodynamics. So it defies the normal laws of the electrical conductivity. It also defies the law of electrodynamics. Okay. So it's something else. That's why we call it superconductor, not an ideal conductor. Because even if you apply the magnetic field in normal state and then cool it down to a superconducting state, still the magnetic field gets expelled from inside it. So which is against the Faraday's law. So that itself, the effect is called Meissner effect. It's not a normal simple. That's why we do not call an ideal conductor. This is something else. This is called, that's why we call it superconductor. And that's we also discussed this if you keep increasing the magnetic field, of course it expels the magnetic field, but above a certain value, value of magnetic field in type 1 superconductor, it becomes normal. It comes into the normal state above a certain field, which is called critical field. So it has two properties. One is related to, as it has two important properties, that the transition, the resistivity is zero below a certain temperature called critical temperature. In the same way, below a certain magnetic field, it remains in superconducting state, that is called critical field. And in the superconducting state, the resistance is zero and the magnetic field inside the superconductor is zero in the type 1 superconductor. Type 2 superconductors are such that there are two critical fields. One is Hc1 and we call it Hc2. Between Hc1 and below Hc1, it's pure superconducting state. Magnetic field cannot penetrate inside the superconductor, but above Hc1, it remains superconducting, but magnetic field can penetrate inside the superconductor, but in a certain way, and in a quantization of a particular value of flux, which we call it this 2.07 into 10 to the power minus 7 Gauss centimeter square. It has to have, like, it flows kind of a vortex.
It's 1630.
Okay, and through which it passes. So those parts through which the magnetic field can pass, that becomes normal state, but other parts remain superconducting. So it's kind of a mixed state. That's what it's essentially called mixed state. And if you go above critical field to Hc2 value, it becomes normal conductor. Normal, it goes into the normal state. So these are kind of essential properties of the superconductor. And as I said, for a long time, the theory or theoretically, this superconducting phenomenon could not be explained because it was discovered in 1911. Till 1956, there was no explanation as such about the superconductor. I mean, it was so absurd that it was not really kind of explained. But in 1956, Bardeen, Cooper, and Schiffer, Bardeen is the one also was responsible for the discovery of the transistor, actually. So he actually received Nobel Prize twice. For that, this is called Bardeen B, Cooper C, and Schiffer S. So BCS theory of superconductivity. So there is a way to explain it, that electrons get bound into pairs with an opposite spin and opposite momentum via electron-phonon, something called electron-phonon interaction. Phonons are nothing but quantized form of the vibrational waves of the background atom. Okay, and these pairs are called Cooper pairs, and they are in phase with each other. So it's a and then they more and more electrons start to form the Cooper pairs, and they come kind of in a phase with each other. So there is a macroscopic phase associated with this superconducting condensate. That's what it is called, superconducting condensate, when all these electrons gets condensed into the Cooper pairs. So they get a single phase. It's like, you can observe the interference phenomena and so on with this superconductivity phenomena at a macroscopic scale. And length scales could be, even in some superconductors, could be very, very large. I mean, hundreds of microns, and even larger than that, the coherence length. And this is the only phenomena through which a practical form of quantum computer has been realized so far. I mean, there are different concepts about the quantum computers, but so far, the quantum qubit has been realized via superconducting. I mean, the only quantum qubit is basically a superconducting qubit made out of the superconducting materials. Different materials, as we discussed, different elements. Most of the elements become superconducting either at ambient conditions, that means ambient pressure, sorry. Usually the TC is very low, and the alloys, some of the alloys would have higher critical temperature, something in the range of 20 to 25 Kelvin. and that's where the BCS superconductivity theory could put a limit for the highest TC that was around 20 of the order of 25 Kelvin. By 1970s, 80s, it was quite realized that was confirmed via BCS theory that the TC cannot go above 25 Kelvin. So it was like more or less things were known. Only research was going on to get more and more alloys superconductors having higher, TC 25 Kelvin, but higher HC critical field also, because that would have direct applications in the high field magnets. So this is essentially still most of the widely accepted application is high field magnet. Usually most of these MRI machines would use are still using superconductors. So this is the chart. I think you can still get this chart also online. So these blue ones are at ambient pressure, and green ones become superconducting at under higher pressure only, the element, and rest remains non-superconducting. So you can see that the materials with higher conductivity like silver, gold, they do not become superconducting even at higher pressure. Similarly, this magnetic elements like cobalt, nickel, iron, of course, becomes superconducting, but still at high pressure, they do not become superconducting. So these were the rules. That's what Bren-Mathias applied these rules, that materials should have high symmetry, high density of states. Oxides would not be superconducting, magnetic materials would not be superconducting, stay away from the insulator, and that's how you can find a new superconductor when the search for the superconductivity was going on within the different alloys materials. Okay, there was 6th rule, that stay away from the theoretician. It was kind of a joke because it was known that, still it's actually true, that you cannot predict theoretically, you cannot predict superconductivity theoretically. You cannot explain, okay, this material was going to be superconductivity, or this would be the TC of that. And still, I think it's true. So these were the two scientists which kind of defied all the rules of the Bren-Mathias, and they discovered a superconductivity in a new material, actually in the oxides, which was primarily also magnetic in parent state. All these 5 rules were kind of defied, and that was till 1980s. Mostly this like how the TC was increasing as a function of years. So by 1980s, we had only superconductors with a TC of roughly around 25 Kelvin. And all of a sudden, this Carl X. Mueller and Bernoulli discovered a superconductivity in this lanthanum barium copper oxide, which is an oxide material. And if you take parent compound, they doped or substituted lanthanum with the barium to certain extent. So parent compound lanthanum copper oxide, LaCuO4, is an antiferromagnetic material. So they doped it. Of course, magnetism was gone, which is still actually that rule is true. So lanthanum barium copper oxide was non-magnetic, but it's oxide, and parent compound, since lanthanum copper oxides, LaCuO4, was magnetic, no one expected that it could be a superconductor. So they worked on it, and they found that the TC is around 38 Kelvin and so on, which was a quite, drastic change in a way, because BCS theory predicted that TC cannot go above 25 Kelvin. So they discovered a material which was kind of defying the prediction of the BCS theory, and it was so, the effect was so much, it was so impactful that within a year they received Nobel Prize for this discovery. And very soon, within a year, some similar kind of compounds were discovered having the TC more than the 77 Kelvin, like this yttrium, barium, copper 07, which is called 123 material, having a TC of 91 Kelvin. Then this bismuth, calcium, strontium, copper oxide, and so on. So this family usually is called as a cuprate family, because essential feature is this copper oxide planes, two-dimensional copper oxide planes within the system, which is an essential feature of all these oxide superconductors. So they are called cuprates, and the maximum is around 135, 136 Kelvin, having this HgBa calcium copper oxide superconductor. So within like 1 or 2 years, it was like the TC was kind of increasing, and at that time it was there was so much of hype that soon we will realize a room temperature superconductor. A lot of funding came in, and there was a lot of research, but these materials are still interesting, and as I said, they received the Nobel Prize for that. Still, we do not know how the superconductivity occurs, because this BC theory cannot be applied to these superconductors. We still do not know how the superconductivity occurs. We do not know the theoretically what is the mechanism. Of course, copper pairs are there, essential features are there, they become zero, they get zero resistivity, they have the Meissner effect and everything like other superconductors. But BCS theory cannot be applied to these superconductors, which we right now know. But we also do not know what essentially leads to the formation of Cooper pairs in these cuprate materials. Now there are other superconductors also, which I have not included in this lecture. There are also something called Nictide superconductors, iron arsenide based superconductors, which were discovered around 2006-7. Highest TC, as far as I remember correctly, is around 55 to 60 Kelvin. So the TC is not that much high. And then there was a recent, there are some discoveries in the which led where the TC is close to 300 Kelvin, but you have to apply very, very high pressure actually. And then there was a very interesting discovery, I think 3-4 years ago from Bangalore, IIC Bangalore. They said they have discovered the room temperature superconductor in gold and iron alloys. So there were some nanoclusters of gold and iron, and in which they said they have discovered the superconductivity. But still, it is not conclusive. I think they have not provided probably the sufficient. It's not really accepted yet that whether it's a superconductivity or not. That is still controversial. So this is kind of a background of the superconductivity in such a way with some essential features. So as I said, there are two essential features of the superconductivity. This is an actual experimental result of this yttrium barium copper oxide 100 nanometer thick film, having the TC of, let's say, like 90 Kelvin, below which it becomes superconducting. And another feature is that above TC, the magnetic field can penetrate through the superconductors, but below critical temperature, a magnetic field gets expelled within the superconductivity. So they do not like each other. It's like there is a kind of magnetic field and superconductivity. It's not compatible with each other. That's what you can think. That's why most of these magnetic materials are not superconducting. So this YBCO, or this cuprate superconductor, which are also called cuprate high temperature superconductor. High temperature, why? Because these are different from this BCS type of superconductors, which limits the TC to be around 25 Kelvin, and they have higher TC like 90 Kelvin, 100 Kelvin. Also, still it's a low temperature compared to the room temperature, but high temperature in comparison to the BCS superconductors. That's what the nomenclature comes from, because this has TC of around 25 Kelvin at the BCS, and most of these cuprate superconductors have TC of the range of like 100 Kelvin, 120, 135 Kelvin, and so on. And with pressure, that TC can be increased up to, like, say, I think 156 or 7 Kelvin, something like that. So what essentially is a feature, most of these superconductors have this copper oxide planes, which is written over here, that CuO planes. Copper is, like, say, this red atoms, and oxygen are this oxygen atoms sitting in this plane, and they make this planes. And you can imagine this to be extended in X, Y, and Z direction. This is something called this is a unit cell of the crystal of a superconductor. So you can think this is one unit cell, and then if you keep repeating in all three directions, you can make a crystal of the YBCU superconductor: yttrium, barium 2, copper 3, O7, and that's what we call it 1, 2, 3 superconductor. So these chains are, these planes are extended through the in X. Let's say if we assume this to be XY plane, so within the XY plane they have this copper oxide planes, CuO2 planes actually. And then along the Z-axis they have these chains, because this one of two oxygen atoms are missing within that plane, so they form a chain. So this copper oxide chains are actually used to dope this copper oxide planes. So as you increase the number of oxygens along this Z-axis, this would start to take the electrons from the copper oxide planes, and the copper oxide plane would be doped. In some other superconductors, it is done by the putting like lanthanum versus barium, because lanthanum is 3+, barium is 2+. So by this way you can dope it, but in this YBCU it is done by this O7, putting some extra oxygen. If you have O6, then this atoms in the along the oxygen atoms in the along the Z-axis, they are not there. So it's basically doping is 0, undoped part, and it is an antiferromagnetic material. As soon as you start to dope, that means you start to put more and more oxygen into this along the Z direction. Then you start to dope the copper oxide planes, and superconductivity starts to appear. Something like, I think, 0.15 holes per CuO2 planes, and the maximum TC occurs at something like 0.25, and then again it starts to decrease. And there are certain, this is something called phase diagram of the usually about the copper pair, something called underdoped, optimally doped, and overdoped. So underdoped also has some features like something called pseudo gap, which I will not discuss here. Then it's not a normal, like a metal, this in the normal state, not a normal metal. Of course, in the undoped part, it's an insulator, but when you dope this copper oxide planes, it becomes metallic. As we can see that as temperature decreases, resistance also decreases. And the highest TC occurs at 0.90 Kelvin, at which we know that it's roughly 0.07. It goes to the transition from non-Fermi, because, and it's linear. That also, it's an indication that the overall metallic part is not a normal, like a Fermi liquid like behavior from this kind of a linearity of the resistance versus temperature part over there, because we know that normal metals are not really, for normal metals, the resistance is not really linear as a function of temperature. So this is an actual YBCO thick film. Okay, another, as I said, this superconductivity and magnetism, they do not go all together, because it's like they have the antagonistic kind of a relation with each other. They do not like each other. So if you use some kind of a magnetic materials, one of the interesting magnetic material with a similar kind of a phase diagram is called something called manganites. Okay, I will not go into the details because it requires a lot of background information, but what I will tell you that these materials undergoes from a paramagnetic to ferromagnetic. They becomes ferromagnetic, something like around 250 Kelvin, one of the member of this family. and at the same time they also becomes from insulating to metal. And if you apply the magnetic field, this transition temperature keeps increasing and resistance also gets decreased. So there is a very large magnetoresistance, negative actually magnetoresistance associated with these compounds around the transition temperature, and that's why these materials are also called colossal magnetoresistance, very large magnetoresistance. They might have applications also. There are also similar kind of material like this high temperature superconductors, similar structure. So that means you can, if you use the artificial way of the growth to make the fabrication in thin film form, you can combine them and see what happens. So you can make a material with the alternating stack of this cuprate superconductor as well as this manganites. And because their structure is same, so you can grow them artificially on top of each other. Okay. So this is possible, as you can see from this kind of this is a transmission electron microscopy picture. This is a substrate, as something called STO, which has also the similar lattice parameter as for the YBCO or LCMO. YBCO is the superconductor, and LCMO is the manganite material. So you can see this unit cells of the YBCO. This is large because along C-axis it has like 11.6 angstrom, and LCMO has lattice constant along C-axis is about 3.87 angstrom. So you can see that this is a large unit cell, which you can see directly over here. Whereas the in-plane lattice constant is almost same for both the materials, which is around 3.9 angstroms. So you can grow artificially these layers, YBCO, LCMO, and so on, superconducting and ferromagnetic. And then you can try to see what happens in this case. So there are different kinds of phenomena which could be observed in this system. What we can also observe that there is a large magnetoresistance, which we call it a kind of giant magnetoresistance, when it goes into the superconducting state only. Then only this kind of a superconducting state is observed, and this only observed when these two LCMO, this is a tri-layer, not multi-layer, like you start with LCMO, YBCO, and LCMO. So when this magnetization of LCMO, both the LCMO layers are anti-parallel to each other, then you see a large magnetoresistance. And in this figure, let's say figure 1a, you can see that the magnetoresistance around this figure 0, this keeps increasing over there and goes away when it is in the normal state over there. But this occurs only, this magnetoresistance occurs when it's close to the transition temperature over there. This is something called photodoping effect. In this, like light does not have that much of impact on the single YBCO film, which is like the graph on the B. It's a slightly underdoped film. That's why the transition temperature is lower. But if you put the light, which is like a small black line, when you put the light, solid line over there, then the change in the transition temperature is very small over there. It does not change that much. But when you have a bilayer, that means two layers, one layer or 12 unit cells of this YBCO and 40 unit cells of LCMO, actually the change in the TC is too large, like approximately like 30 Kelvin and so. So there are some unusual effects which can be, which we cannot even predict that's going to happen, which happens in this kind of a multi-layers. We also see certain kind of an effect like this magnetization of LCMO as we go into the superconducting state starts to modulate. In one layer, if you have like a multi-layer, 10 layers of YBCO, 10 layers of LCMO, and you magnetize it, and then you go into the lower than the superconducting temperature, then in one layer, this magnetization starts to decrease, and another layer starts to increase. So there is kind of a modulation of this LCMO. So there is an effect, not only the magnetism effect. What is the essential takeaway from this slide? That usually it was known that superconductivity is affected by the magnetism, but here what we see is that magnetism also can get affected by the superconductivity. How do we make these films? How do we grow this kind of artificial layer? One way is something called this pulse laser deposition technique. What you have is something called target. So you take a polycrystalline target, you make essentially a YBCO thick kind of a palette, and then you put a laser pulse on this target, very high intense laser pulse, which you focus it in a small spot size. So most of the energy is concentrated on a very small spot size. So the electric field of the laser pulse is very, very high. And due to that electric field, the breakdown occurs in this palette, polycrystalline palette. And due to this dielectric background, electrons go away, and rest of the remaining part is the background ions of the sitting ions in the solid. And as these electrons start to follow the electric field of the laser pulse, it starts to get collision with the background atoms, and this whole crystal gets all the bonds starts to break, and these atoms or ions comes into the vaporized form, and they form a plasma. Plasma is essentially nothing but a mixture of the neutral atoms, ions, electrons, and this is something called plasma plume. That's what it is coming after that. And if you have a low pressure inside there is a chamber, something like this, which you can see on the right bottom. If there is a vacuum inside it, once this plasma plume is formed, it starts to kind of expand. And if you place your substrate over which you want to grow your material, this plume will reach to this substrate, and this will start to grow in a crystalline form, like in a single crystal way over the substrate. So there are certain advantages of this pulse laser deposition compared to other growth technique, because these high temperature superconductors or these manganite materials have a lot of elements. So for a single element, a material having single or binary kind of an alloy, that is still easier to grow with different other techniques. But pulse laser deposition can transfer the same structure, but because you want to transfer the stoichiometry also from your target to the substrate, like yttrium having one element, one atom, barium 2, copper 3O7. So in that way, usually it's very difficult for other techniques. This technique is quite successful in a way to transfer the stoichiometry of the target to the substrate. So this whole film can be all the stoichiometry with the same crystal structure can be transferred. Okay, I don't want to show it. And what you essentially can do is also you can using something called electron diffraction, you can grow it layer by layer. Like one unit cell is formed, then second unit cell, then you can always control where do you want to stop it. So this is an electron diffraction spots on a camera. You take an electron gun from the surface, it gets diffracted, and then you see these are something called diffraction spots. You will study about the X-ray diffraction or electron diffraction later on in the various courses. So this gives you the symmetry of the atoms of your surface. So directly this spacing between these spots is related to the interatomic distances actually. So you can calculate what is the interatomic distances, or what is the symmetry, whether the your atoms are sitting on a square lattice or a rectangular lattice or hexagonal lattice. By the symmetry you can find it out, and also by the spacing between them you can find out the atomic spacing also between your on the surface of your material. So if you start to observe the intensity as a function of time as it grows, you can see on the right hand side of the bottom of the screen, like say figure B, the intensity goes down and then comes up, goes down, comes back up. So between the two maximas, actually one unit cell is formed over there. So you can in situ monitor the thickness, you can in situ monitor the roughness, you can in situ control actually the growth, whether you want to grow 3 unit cells, 4 unit cells, 3 layers, 4 layers, 5 layers. So that's what all these things can be measured over here, also in this electron diffraction phenomena. Similarly, like now you can grow the other layer, so that's what we grew, this YBCO LCMO 10 nanometer into 10 times by layer, and this acts from the X-ray diffraction or neutron reflectivity. You can find out the information, the thickness, bilayer thickness, whether the bilayer has formed or not, what is the individual thickness. All this information could be we could also get. And then we can of course do the resistivity measurement, and then you can see that we can easily get this relation. So you can see that these are nicely grown YBCO and LCMO films, and up to the large scales over there. So these are kind of artificial lattices which you can grow of different thicknesses. YBCO, one unit cell given by this red rectangular kind of uh, box on this, and these are like chains over there, which I was talking about, this marked by the arrows. These are the chains over there, and this is the LCMO film. So these are all atoms, different atoms, which you can see this contrast in the black and grayish contrast, different atoms, or giving idea from the different Z numbers. So the higher the Z number, higher is the contrast. Just give me a, sorry, I'm just, I have to take this call. Hello. हेलो. हाँ हाँ हाँ, कर रहा हूँ मैं, 1 मिनट करता हूँ कॉल. ठीक है, कर रहा हूँ. हाँ ठीक. Okay, so yeah, this is the transmission electron microscopy picture. So what we can do is we can grow this.
It's 17 hours.
Layers of different thicknesses, YBCO, LCMO, like 13 unit cell. But what we observed also, that at the boundary we do not have the chains at the interfaces of this YBCO LCMO. It grows in the between. Let's say we grow 2 unit cells of YBCO, then only there would be only one chain. If we try to grow only 1 unit cell, there would not be any chain, and chains are responsible for the doping. So that means that it's not possible to grow one a unit cell. It's not possible to get superconductivity within the YBC, 1 unit cell of YBCO. Whether then in 2 unit cells it should be possible. So that's what we did, and we could find out that okay, with YBC 4 layer of YBCO, it's superconducting. 3 layers, of course, superconducting. 2 layers are also superconducting, but so with 1 layer, it's not really superconducting. So this was all about this presentation. What now I can show you some. Let me see if I can show you a movie also about this superconductivity phenomena. You would probably like it. Just let me check presentation. Just wait a second. Let me try to find out the movie. Um, Wait a second. Wait a second. Just give me a second. There's some issue with the. Meanwhile, I start another movie for you, and you can probably look into that. Meanwhile, I will try to fix it if. Presentation. Okay, so let me start sharing the screen. So I think you can see it. What essentially it is like a flash dance, which is also available on YouTube. It shows how the like Cooper pairs are formed, and through this flash dance, and how do they move, and as temperature decreases, as they start to form, how the superconductivity is created, and how do they behave through this time. Just wait a second. Yeah, so that's what it gives a kind of a feeling. I think you can also see. Meanwhile, I try to look this another documentary if I can kind of fix it. Sorry, I think. Oh, I started to. Maybe I should wait. He's trying to.
Sont des oxydes à base de céramique.
Used today in hospitals.
En industriel,
Candidates.
vient de mettre au point un instrument de détection du cancer du sein. Lui, pouvoir supporter
Make their way.
So more and more, like you go down into the temperature, there is more and more kind of synchronization between the different core pairs, and they start to become more and more into kind of a phase with each other. And that's what the phase is same. And then this phase can be, because it's kind of it becomes kind of a macroscopic phase. Because in the usually materials, the phase from one electron to another would differ, and through the scattering event, so it's not possible to do like the quantum computation. But if you have a macroscopic one single phase, that can be utilized for this quantum computing actually. So that's like now the current starts to flow